In this video, we'll be discussing what's called a random walk, and in particular, a famous probability theory problem, which is the gambler's ruin. This is in my opinion, a simpler variant, but it gives you a taste of how these random walks go. So here's the problem. A gambler has $1 left before he goes bankrupt. Each game he plays, he wins $1 with probability P and loses $1 with probability 1 minus P. And we're just go ahead and going to call this equal to Q, just so I don't have to keep writing 1 minus P. It's called a random walk because some features of a random walk include that you kind of go up and down in value. So he's going up $1 or down $1. And it's random in the sense that each move he makes is independent of the previous move, and it is a random move. He doesn't have full control over it. Okay, so what is the probability that he goes bankrupt in 5 games or less? That's our question we're going to answer. And so through this problem, you'll get a good practice of your multiplication rule and just thinking sequentially through a problem that on the surface seems pretty difficult, but if we break it down into smaller problems, it can be done quickly. All right, so I made a grid here to visualize us, which is a really good problem solving technique. We have dollars left, so we're starting right here at 1. And then we have our games played as we move down the tree. So usually I draw the tree left to right. This one I'm going to do bottom top, doesn't matter. So we're starting at $1 left. What can happen at that $1? Well, we could lose, or we could win a game. And there's where we're going to end up. We either are going to end up at 0 or we're going to end up at 2. And that's after 1 game played. So here's your win. And here's your loss. Or sorry, that's your loss. And that's your win. And actually here is really game over. So the whole gambling day could end right there. So that's when he can go bankrupt right there. But he could not, right? He could have won that first game. And that second game, he could win. He could also, not win that game. He could lose that second game. And then he could win this game here. Okay. And right now, neither of them have us bankrupt yet, so I guess it's not possible to lose on the second game played or to go bankrupt in the second game. Okay, we'll continue on. Then we could say, let's go here. That's if we lose again. And here. That's if we win. Same with here, we could say we lose here. We could say we win here. So what seems to get a little complicated is now that like this W and L here, they seem to share a space, but so maybe we should do a better notation. We should maybe start labeling the roots with what's happening. Okay, but either case, on this position right here, we're not bankrupt yet. We still have $2. But on this position here, we have gone bankrupt. So I'm going to mark that with a sad face. Okay. And let's see, is it possible for us to go bankrupt by the 4th game? It actually doesn't look like it. We'll take this one here though. We'll say, okay, you can go here. So that's a loss. Or you go here, which is a win. You go loss here, or you could go win here. All right, so I don't think by the 4th game it's possible for us to go bankrupt no matter what scenario we've placed ourselves in. But I think by the 5th game we have a couple different scenarios. So let's go here. So that's a loss, and we've gone bankrupt because we are now in the bankrupt column. Right, we have $0 left. So that's a bankrupt scenario. So I'll put a square around it. Are there any others? Well, this one here, you're not bankrupt. Let's see. Okay. I don't think any of these are going to lead to bankrupts, right? We did go there. There. So as you can see, the tree builds out a lot out in this area, but we're just counting the ones that take us to bankrupt. So I'm going to start highlighting them. It looks like we got a couple paths that we can take. So we have this blue one here. What's the probability of that happening? Well, that's just on the very first game. Well, he's already played a lot of games, but he has $1 left, and on the very first game, he loses, and that happens with probability 1 minus p. All right. Let's see, how do we get to this loss here? Well, we have to go win, and then lose. That takes us here. So we have 1 minus p, and p. So that's a path. So I could say one such way is you lose in one game, or go bankrupt in one game. The probability of that happening is 1 minus p. You go bankrupt in 3 games, and that's happening with probability p times 1 minus p squared. Is there any other ones that lead us to that path? I think that's the only one. Yep. Okay. And then we also need to get down here on 5. And that's happening, let's see, I can go this way. Okay, so that's one path, so I need to count that. So let's calculate that. That means I have a p here, and then total there, so I have p and p. And then I also have 1, 2, 3, 4. 1 minus p, no, sorry, not 4, 3, 1 minus p, 3. All right, I have p, 1 minus p, p, 1 minus p, 1 minus p. All right. And then I can also go, I think I can go one more way. I can go here, here, boom, boom, boom. Yep. So I already just did this, sorry, I just did this one. And now I can also go double p and then triple loss, which is the same, right? Plus p times 1 minus p cubed. All right, and there's no other ways to get to loss in 5 games or less, so probability bankrupt in 5 games or less equals a probability bankrupt in 1 game plus probability bankrupt in 3 games plus probability bankrupt in 5 games, which is 1 minus p plus p times 1 minus p squared plus 2 p squared 1 minus p cubed. And that's it. So this is just a small variant of a more well-known gambler's ruin problem. But in either case, this should give you a good preparation for a random walk problem that you have to do in your problem set. In either way, visualizing with a tree diagram and just visualizing the outcomes that you want to capture in your probability are going to be good enough for the computation. I'll see you in the next video.